Topology rules are basically um, just a set of statements that guide or explain the interaction between features. An example would be adjacent polygons must share a coincident boundary that is exactly the same for both. There are no gaps or overlaps between adjacent polygons. And all that says is that if there's two polygons that are adjacent, you can't have those overlaps like where green goes over orange or gaps where orange doesn't meet green. And then it has to be like the one you see on the right where they have a coincident boundary. Second one would be things like lines should always end on other lines. Failures of two lines to meet is called a dangle. Undershoots occur when a line is not quite long enough. Overshoots occur when one is too long. If you have a node or endpoint at the intersection, lines crossing without nodes are termed improper intersections. Lines intersect a node where there are only two lines meeting is called a pseudonode. And they don't really impede your analysis, and so they're no big deal. Some are a minor annoyance. The errors show up when you zoom in. It makes your maps look a little wonky. That's not good. Others are analysis stoppers. These are errors that prevent analysis functions from working correctly. Things like utility networks, because the lines aren't connecting properly, and so it doesn't actually perform as a network the way it's supposed to. Um, Errors can also complicate spatial queries because relationships that you're querying off of aren't actually correct physically, so that's an issue. And then, of course, legal issues and liabilities, things like parcel boundaries and overlaps. Um, while the county may benefit from two people paying taxes on the same property, two people thinking they own the same thing is a bad situation. So topology problems can be, everything from you don't even know they're there to someone's getting sued. Situations, dead end streets, um, overpasses and underpasses. We've talked about those. The question of topology, it is how well the features mimic the relationships in the real world. If they don't reflect the real world and can be fixed, they should be fixed. If they don't reflect the real world and they're not avoidable, we would call that an exception. We do what we can to maintain logical consistency. Our data is sort of lumped into two types of models. The first one we're going to talk about is a spaghetti model. Spaghetti models don't store any topology. In other words, there are no rules for interactions between features in a spaghetti model. This would be shapefiles and feature classes in some geodatabases. There are no tools for testing logical consistency. There's just simple tools for creating consistent features. Snapping, autocomplete, cut polygon, map topology. Map topology is um, something different from just topology in general. These are the things that we're stuck with in spaghetti model. And a spaghetti model, the reason they call it this is it's like a plate full of spaghetti where each noodle is simply a noodle and it doesn't care what the other noodles are doing, and it can go up and around and over, and there's just no rules or anything logical about it. Okay? Another type of model is a topological model. Topological models store topology, and allow settings of rules to govern the topology. In other words, you can have rules like county polygon must not have overlaps or must not have gaps. Um, you can set these things, and so once you've got this data put together and you test these rules, it will find any places that violate the rules, allowing you to then go back and fix those. They use two basic techniques: divide and conquer. Start by creating a square outside boundary and then use the cut polygon tool to basically carve out one polygon at a time, building off of an existing polygon. That way you don't have any gaps and overlaps and all your boundaries are coincident. The next method is the add territory method. You use it to create new for the first polygon and then you auto complete for most of the rest. It's still basically the same kind of scenario. Well, if you look by these green boxes, it'll point out where some of the things are. Up here at the top, if you're not careful, 4 and 6, you might want to merge them together because that might be a spot there at that point where it's challenging to digitize it. Maybe you want to make point 3 there before you go on to do number 5, or maybe you make 5 and then carve 3 out. Doesn't matter. Number 11 there, you might want to chunk that out of 7B before you do anything else. They tell you to learn by experience and not get painted into a corner. I like to think of it as thinking yourself into a corner, to where you don't see any way out without screwing up a bunch of work you've already done. Digitizing effectively and efficiently takes a lot of time and effort. You simply got to do it until you make enough mistakes that you don't make the mistakes anymore. And you have to get comfortable and familiar enough with the tools to do this. Now, when you do the tutorials on these chapters, it's going to give you a layer of geology and it's going to ask you to digitize it. You do not need to spend the 2 or 3 hours it's going to take to digitize all of that data. But you need to do enough that you're comfortable with what you're doing and you're comfortable using the different tools that Price has shown you how to use. Once you get to that point, as far as I'm concerned, you can stop digitizing and move on to the next part of the assignment or the tutorial. But again, don't digitize 2 or 3 polygons and say, I got this. And don't digitize all of it because it's what it tells you to do. The goal is for you to become comfortable using these tools. If that takes you doing all of them, then do all of them. If it takes you doing significantly less than all of them, that's fine. But don't cop out and say, oh, I did a couple and I'm good. No. Do at least a third of them. All right? Features and attributes, it removes common boundaries if they're adjacent, and pieces may be adjacent or disjointed. And so if they overlap, it becomes a single thing. If they don't overlap, it becomes a multi-part single thing. Union, similar to merge, but it gives you a new feature. Doesn't change your original. All the attributes are ignored. It just gives you the shape. Lines or polygons. The target layer determines the output. Basically, it creates a new boundary, a specific distance from an existing feature. That's all buffering does.